Let's look at some properties of the DQN algorithm. First of all, DQN is model-free. That is, it solves the reinforcement learning test directly using samples from the emulator, from the environment, without explicitly learning an estimate of the environment, right? So it is a model-free algorithm. It is also off policy. It learns the optimal policy, the one that maximizes the Q values, or returns the actions that maximize the Q values at each state, while following a different behavioral policy, right? So the behavioral policy is usually one that ensures adequate exploration of the state space, for instance, epsilon greedy. Let's take a look at the idea of experience replay, which was presented in this paper. So using such experience replay has several advantages that are important to discuss, because after DQN, most of the state-of-the-art algorithms still make use of experience replay. So this idea is general enough that it is commonly used in many of the state-of-the-art algorithms and in actor-critiqued algorithms, and we'll discuss it over and over again. So it might be beneficial for us to take a second and discuss the benefits. Why is an experience replay buffer so beneficial? So we saw that each step of experience is potentially used in many weight updates, right? We had the random mini batches that we sampled. And this allows for greater data efficiency, right? So that might address the issue where for training deep neural networks we need a lot of data, which we don't necessarily have in reinforcement learning, because these are just interactions with the environment, which might be costly. So by reusing data from our experience, this allows us to dramatically inflate our training data size, our available training samples. Next, learning directly from consecutive samples is inefficient, right? We discussed that. This is known in machine learning, in supervised machine learning, because of the strong correlation between the samples, which are, as I said, usually bad in machine learning. Randomizing the samples breaks these correlations and therefore reduces the variance of the updates, right? So the large experience replay buffer allows us to randomly sample transitions from different episodes in different time steps, right? And that allows us to decorrelate the samples. Finally, the behavior distribution is averaged over many of the previous states and previous episodes, smoothing out learning and avoiding oscillation or divergence in parameters. Okay, so again, this helps us with not committing for a specific state and action space distribution, right? But provides us with a larger high entropy distribution over the state and action space, because we sample from many different episodes with some level of random exploration. Okay, finally, you should note that when learning by experience replay, it is necessary to learn off policy, because our current parameters are different to those used to generate the samples. And this further motivates the choice of Q learning, specifically one-step Q learning, unlike eligibility traces, which is on policy and might be an issue here. But as I said earlier, one might consider merging the two, although it will require you to also augment the experience replay buffer. Now you'll have to also consider not single transitions, but full episodes. You could do that, but it requires some extra bookkeeping, I would say. But you can definitely do this merge of eligibility traces within DQN. Okay, so continuing with this experience replay buffer, DQN only stores the last, right, as we discussed in the pseudocode, it only stores the last n experience tuples in the replay memory. All transitions are eventually overwritten, right, based on the size of your replay buffer, on your n hyperparameter value. Samples are uniformly and randomly drawn from the buffer, and when we perform each one of the training updates at each time step. Is there room for improvement? Sure, and there are improvements that were presented along the years, right? For instance, you can decide or you can somehow prioritize the experience and maybe sample important transitions more often, right? What are important transitions? What would you say is an important transition?
Whether not seen before, not trained before.
Maybe those that were less seen before, but that can be resolved if you have uniform distribution, right? Uniform distribution can somehow allow you that everything will be eventually sampled. But we discussed prioritized value iteration, right? Previously, when we said, hey, maybe we want to update some transitions more frequently. Which one? Maybe those with the larger TD error, for instance, right? Because if we'll update them, well, we'll be able to address more of our existing TD error. And there are different solutions there that might be considered, but sure, there is room for improvement, right? And you might want to implement that in your project and report to us how different improvements work in different situations.
But would such a prioritized buffer still not keep the samples independent and not correlated?
So you'll have to take care of that, right? You have to be sure that you're not prioritizing correlated observations or successive samples, right? Sure, if you set a specific priority, it might somehow prefer correlated observations, so you want to avoid that, right? That might lead to instability. But this is why we think about things or ideas and try them out, right? This is how we experiment. And then there's also a question where you can prioritize your replay, your samples. You can also prioritize deletions from the replay memory. So if your replay memory is of size n, commonly, or the pseudocode that we just saw just deletes old transitions, but you might say, I don't want to necessarily delete all transitions because they include some important information and I'd prefer to delete other transitions, other samples. That's also fine. If you want to read more about solutions that people have tried before, you might want to look at the paper that is linked here that discusses prioritized experience replay. Okay, so let's see some examples for how DQN performs in the Atari environment. So this is the Sequest domain, a specific game. And this is after 500,000 episodes, training episodes. And you can see that the submarine becomes a bit better in shooting the fish. So this is a bit of a complicated game, right? You need to shoot not the fish, you have to shoot the other submarines, collect the divers. Do you shoot the fish? Or you have to avoid the fish? And you have to keep your oxygen from running out. So it's not straightforward, and you can see that still the RL over time learns to perform better and better and with longer horizon. So you see that it is now able to perform pretty well, but its oxygen is running out. So it still didn't learn to surface and replenish its oxygen. But after it will be trained for long enough and will propagate Q values over longer trajectories, over longer horizons, it will also learn that it should surface and replenish its oxygens. Ah, you see, yeah, got there now. Okay, so, and it's important to remember that it learned only from pixels, from game pixels, right? So no one told it, what is this game, what is a submarine, what is the oxygen and the fish and anything like that. It just learned by trying, looking at the pixels, trying different actions, and observing the change in score. You see, it's playing pretty well. So let's see another example, because as I said, they used the exact same training algorithm. DQN was exactly the same. And they had to retrain it, of course, for each game, but they used the exact same algorithm, the exact same code, to train it over various games, all from the Atari video games. And so this is when they applied the same training technique, with the same deep neural networks, so no expert knowledge, for playing a different game. So this is the Space Invader games, where you have to avoid being shot by the alien and shoot all of the aliens down. And you can see that over time it performs better and better. Oh, so this is the trained policy already. So you can see that after training it can perform pretty well. Okay, and here are the training curves for exactly these two domains. So on the left, that's the Space Invader that we just saw. That's A, here, yeah, that's Space Invader. And B is the Sequest domain that we saw before the Space Invaders. Each point is the average score achieved per episode. And you see the x-axis is the number of training episodes. So, and here they ran DQN, the same algorithm that we discussed previously, with epsilon greedy policy. The epsilon was set to 0.05. And yeah, right, as I said, these are just the training curve. You can see that over time the average score per episode, well, increases. It is able to play better and better. So as expected, the training curves have an upwards trend. It is learning. So they also reported the average predicted action value on a held out set of states on Space Invaders and Sequest. And you can see that over time it is able to improve the Q estimation for these states, for general states that it didn't see during training, right? So you can see that it is both able to generalize the knowledge, to be able to do good prediction for states and action pairs that were not seen during training, or not exactly seen during training, right? It saw similar maybe states and actions, but not exactly those state and actions. And you can also see that over time the Q values, the Q estimation go up. Why is that the case? Any idea? So the Q estimation is based also on the specific state and action pair that you're estimating for, but then assuming that you take the optimal policy based on the Q values moving forward. So over time, your policy moving forward, right, after a specific state and action pair, also improve, because better Q values imply a better policy. And so this is why you see an upward trend in the Q values following the improvement in the policy, in the learned policy. And you can also see that the Q value, so we don't have any convergence guarantees for DQN, but you can see that in practice, it does show some convergence trends. By the way, you need a lot of tricks and a lot of hyperparameter tuning in order to get convergence in learning. But you can see that it is achievable at least, right? At least in these two domains, they do show that they are able to reach convergence behavior for the Q values. And eventually they ran the same algorithm on many different Atari video games, and they reported the results for each one of them. And these results are normalized between a professional human game tester, not sure how they defined it, I don't know, someone that plays a lot of video games, I guess. So the professional video game tester is the 100%. So for instance, let's see, in Time Pilot, you see that DQN reached 100% performance. This means that it reached the same level of performance as the professional player. Okay, anything above 100%, it means that it was able to perform better than an expert human. Anything below is below human level. Okay. All right. In the paper, they provided results for running DQN, as we just saw it, the same code, the same algorithm on many different video games from the Atari framework, and they report results for each one of these domains, where the reported results are after convergence, after training the DQN, and they are in relations to a professional human game tester. I'm not sure how they define that, probably someone that plays a lot of video games. So they looked at the score of a professional player versus the trained DQN policy. And these are the results that presented here. On blue, you see the results for DQN, for the DQN algorithm, as we just saw. And the gray values are results for the best linear learners. So without a deep neural network as an approximator, just as a linear approximator. Right? And obviously that was not able to perform well in most cases, although there are some outliers. One outlier, oh sorry, maybe two outliers. The double dunk and maybe the gravitar here. But in any case, you can see that for many of these games, the DQN agent was able to perform at or better than the human expert. Okay, so we were able to use this general algorithm to train a policy that plays video games by just looking at the screen better than an expert human. And you might also ask yourself, what's going on in these domains where it isn't able to perform very well? And moreover, specifically, let's look at this domain, Montezuma's Revenge. So in this domain, the DQN agent was not able to perform better than a random policy. Right? It reached 0%. 0% is at the level of random play. So let's take a second to look at this domain. Oh, so these are the domains. Oh, so we actually have 4 domains where the best linear learner was able to outperform the deep neural networks. I would guess this is because of the stability provided by a linear approximator in domains where it is sufficient to learn an optimized policy. Okay, where the low-level features are actually pretty easy to extract from the pixel. So let's take a look, as I said earlier, at this outlier, this special outlier, Montezuma's Revenge domain, where the DQN agent was not able to perform better than randomly hitting buttons. And the reason, if we observe this game, Montezuma's Revenge is like a quest where we have a figure here that needs to avoid obstacles and get a key and then get some sword and obtain some stuff, and only once it gets the key it can go and search for an exit, or once it has the sword it can do stuff. And this is known as, first of all, a long-term planning problem, where you have to have a specific sequence of actions, a very specific sequence of, a long sequence of actions, and only at the end of that will you be able to observe some reward that relates to that long sequence. And also this is known as a sparse reward problem, where you only observe the reward after you perform this long sequence of actions. And these types of domains, long-term planning and sparse rewards domains, challenging for reinforcement learning algorithms, and usually they require special tricks, special algorithms that are specifically designed for long-term planning and sparse rewards in order to successfully address those. But DQN is not, at least the vanilla version of DQN is not appropriate for long-term planning and sparse rewards domain, as we saw in the results.